Hi everyone, welcome to Chapter 7, which will cover bone tissue. Now, Chapter 7 is going to be the preload, or I should say the starting chapter, that will start introducing us to the skeletal system. Now, when you hear that term, I think many of us will think about things like all the different bones that we find in our body, but we'll also have to discuss things like cartilages and ligaments. Cartilages, because oftentimes they tend to be the forerunner of most bones. So when we take a look, for instance, at embryonic development and the fetal skeletal, we see that most of it is composed of hyaline cartilage before that's replaced with the actual bone tissue. The ligaments and the tendons will also need to be discussed because they're going to be essential for the support system. As you can see on your slide, right towards the bottom, ligaments have an extremely important function where they will go ahead and anchor the bones together at joints, whereas the tendons will focus more on attaching muscles to bones. Part of what we'll also have to do in the skeletal system is obviously naming all these different bones that we have in our system. And in fact, that's what we're going to concentrate on in Chapter 8. In Chapter 7, we're going to focus a little bit more on bone, as in the tissue that makes up the bone organ. Now, bone tissue or osseous tissue is an example of connective tissue. This we came across in Chapter 5. And what makes bone tissue so unique is the fact that its matrix, its background, becomes hardened mostly by calcium phosphates as well as by other ions and minerals. But the hardening of the calcium phosphate is what gives rise to the process called calcification or mineralization. And the whole purpose of this is to harden the surrounding of the bone so that it can provide the support and leverage that are needed for the body to maintain its homeostasis. Now, one thing you want to keep in mind is that when we start looking at the individual bones, so now we've upgraded from bones as tissue, but now start looking at bones as in organs. So for instance, the femur bone, the humerus bone, the clavicle bones, all the bones that make up your skull, you want to keep in mind that those bones are classified as organs, which means that they will be composed of different tissues and components. So you'll have your osseous tissue, your bone tissue, you'll have your bone marrow, you'll have your cartilages, and along the way you'll also have other tissue types, because remember, as I mentioned to you before in Chapter 5, organs are composed of several tissue types. You'll also have other connective tissues make an appearance, such as your adipose tissue, your nervous tissue, as well as some of the fibrous connective tissues that we've previously discussed. There are many different ways to go about classifying bones. So what I want to do is, before we actually get into the hardening or the calcification of bone, I want to talk to you a little bit about the classification methods that you're going to come across. And these are important to point out because each of them will have specific terms to label the particular bones that we're looking at. Now, many times we can take a look at the overall morphology or shape of the bone, and we can tell that based on general features, we can label the bone based on it being a flat bone, a long bone, a short bone, or an irregular bone. This classification will have everything to do with the overall shape of the bone. So let's start on top of our slide, and I inserted a very simplistic picture of a skeletal system on your right hand side, and as you can see, some of the bones have been labeled out. Look at the blue arrows. So let's start with a flat bone. A flat bone, it's all in the name, it's going to be a bone that is relatively thin. It is going to most likely tend to cover or protect soft organs. It tends to have a little bit of a curved plate to it, and probably the best example of a flat bone are all the bones that we actually find within our skull. So in a little bit, we're going to talk about, for instance, how you have the bone that makes up the forehead, that's your frontal bone, the bones that make up the back of your skull, that's your occipital bone, and then the bones that make up the side of the skull, those are the parietal and the temporal bones. Those bones are all examples of very flat bones. On our picture that I've inserted, you've noticed that they do mention another example of a flat bone, and that's going to be the sternum. That is going to be our breastplate bone. So if you take your hand and you press down on your chest right below your throat, you're going to feel the sternum. That is your breastplate bone. It is a very flat, curved bone. Now, another classification is going to be a long bone. A long bone means that when you look at its morphology, it's going to be elongated. So it's almost going to look like a rectangular shape. It's going to be longer than it's wider. And probably the best example are going to be those bones like the humerus and the femur. The humerus makes up the top part of your arm, and the femur, which is the one that the picture highlights, makes up the top part of your leg. As you can see, both of the bones that I just recently circled are very elongated. Long bones are really good at acting as a lever, so oftentimes your body will utilize them in conjunction with muscles to allow for a full range of movement to occur. So anytime that you are lifting or extending your hand, what you're utilizing is the lever ability of these long bones. Now, if you have a long bone, that would also mean that you should have a short bone. So a short bone is going to be a bone that tends to have more of a cube or a circular shape. They tend to be equal when it comes to comparing the length or the width. And this basically allows the bones to easily stack on top of each other and glide. So for instance, when we take a look at all the bones, like our carpals and our tarsals, which are the tiny bones that make up our wrists and our ankles right over here, you can see the little cuneiforms have been identified. Those bones are very cuboidal or cube-like in shape. So they're an example of a short bone. Now, I know I listed some of the bones. If you're not familiar with them, please don't worry about it. Like I said, chapter 8, which is our following chapter, I'll have lots more pictures and I'll be labeling the bones as we kind of go from the top of your skull all the way down to your phalanges, which are going to be your little toes. So this is just a quick little intro to take a look at some of the more common bones based on their morphology. Our last category for classifying bones this way is if you have a bone that is neither flat, long, or short, we have a miscellaneous category, and that's going to be called an irregular bone. So an irregular bone tends to have a very abstract type of shape, a very unique type of shape. One that I can think of is a bone called the sphenoid bone, which almost looks like a little butterfly. It sits within the cranium cavity. So when we look at our skull, you'll be able to explore it. You also have another bone in your skull called the ethmoid bone that looks a little spongy. It almost looks like a rock that has lots of cavities embedded into it. But a more common bone that I hope many of us have at least seen once before is a vertebra. So here, let me draw my little arrow. The vertebra bones are the bones that stack up and make up your spine or protect your spine. As you can see, it's a very irregular shape to it. It's neither long or short, and it's definitely not flat. So that would be an example of an irregular bone. I also just noticed that on the picture that I inserted, they mention a sesamoid bone. A sesamoid bone is a bone that develops due to stress being applied to that region. And your patella, your kneecap, is an example of a sesamoid bone. Babies are not born with kneecaps. They will only start developing when the baby starts to crawl, and as pressure is being applied on the legs as they are moving around, we see that that stress will induce the formation of the patella. Your little kneecap. So that's an example of a sesamoid bone, a bone that develops due to stress being applied in a particular region. Another classification when we look at bones that you're going to hear a lot is me mentioning a compact bone versus a spongy bone. So let's talk about that one next. Now, on your right-hand side, I've inserted a picture of the femur bone. So this is that big bone that makes up the top part of the leg, and I'm going to put a little circle around it so we all know what we're talking about. And I think for many of us, when we envision learning bones, this is the image that we have. We have a bone that's sort of solid in its white color. It's elongated on the outside. It has a very dense shell. It's homologous in coloration, nice and solid. And when you see this happening, that's because we kind of classify it as a compact structure, meaning it's very dense, very solid, homologous in its overall colors. However, if we were to cut open the bone, what we would see is that certain parts will maintain that solid and density of the compact bone, but some parts will also start to look a little bit like a kitchen sponge, in the fact that they will have small little cavities, small little caves within the bone itself, and it almost looks like there's little strings all over the place. Now, when you see that particular feature in the bone, so the one that I've circled right over here, that is then going to be classified as a spongy bone. And the spongy bone gets its texture because the bone tissue is not as compact or highly organized as we see it with the compact bone, which tends to be more of an outer shell. It is very common for bones to have a mixture of compact and spongy bone tissue. The ratio as well as the location of each will obviously vary depending on what particular bone you're looking at. But when you look at a long bone, it tends to be very common that the center of the ends as well as the shaft region, the middle section of the bone, will be spongy bone, whereas the outer part, the covering, will be more compact with obviously the compact bone. Over here it has a little statement. It says the skeletal system typically is about 75% compact and 25% spongy. Now, speaking of compact bone, or speaking of our little femur over here, let's take a look at some of the more common structures that you're going to come across on a long bone. So the next section we want to talk about is called long bone features. And I'm going to show you an illustration in a slide or two, so please bear with me. But I want to introduce you to the terms first, and then we're going to try to match them on the image. The first term to take a look at when you're looking at a long bone is the diaphysis. The diaphysis is going to be the shaft region. I'm going to go ahead and erase this real quick and switch to a different color so I can highlight this for you. This elongated section of the femur that I'm boxing in, this is my shaft region, my diaphysis. Inside of it, we're going to see that when we cut open the femur bone, we're going to have a little cavity on the inside, a little dip. This is called the medullary cavity, and in fact, you can see a little bit of it over here appearing. It hollows out. The medullary cavity is also called the marrow cavity because it can be filled with either yellow marrow or red marrow, depending on what stage of development the body is in. We're going to talk more about that. The epiphyses are going to be the end parts of the long bone. So I'm going to switch over to yellow. I'm going to go back over to my femur on top, and I'm going to circle for you the edges of the long bone, and these will be my epiphyses. Now, when I say it, I sound really weird, and this is due to my lisp, so please forgive me, but that is going to be the epiphysis. There's nothing I can do about it. This is my speech. All right, now that's going to be the epi region. That's going to be the end parts of the bone. Part of what we have to discuss is going to be what exactly covers these particular sections. So let's go over to our next slide. And over here, it's going to tell us that we have articular cartilage, and this is going to be a very thin layer of hyaline cartilage that's going to be covering the episections, or the end parts of the long bone feature. And this allows for, whenever you put cartilage on top of the surface of the bone, it makes it easier for the joints to interact with each other and glide over each other. So it almost provides like a lubricating event. The shaft section, so the diaphysis of the long bone, is not going to be covered with articular cartilage, but instead it's going to be covered by a membrane called the periosteum. And the periosteum, as you see on your PowerPoint, it says it's the external sheet or covering that will take cover of the diaphysis, or the shaft region of the bone. It has an outer section that's mostly collagen. Remember, collagen fiber gives us lots of strength and durability. And it has an inner region that is full of osteogenic cells. Now, osteogenic cells basically indicates the fact that these are going to be cells that are allowing us to build up the bone and form it and obviously remodel if needed. We're going to talk about that term in a little bit when we start looking at the different bone forming cells that your body has. The endosteum is another membrane that we find in the shaft region, but this is going to be in the internal part. It's going to be lining the medullary cavity that we find inside of the shaft. This one is mostly made out of reticular connective tissue, but either way we see that very similar to the periosteum, the endosteum will also have access to bone forming cells so that it can continuously monitor as well as start remodeling the bones if need be. Now, it's important for me to kind of highlight this for you. Since bones are organs, you want to keep in mind that they're going to have nutritional demands as well as build up waste products, but also they will be continuously remodeling themselves depending on the stresses and the use that are being placed on them. So your bone, as in the organ of the bone, is consistently breaking down and rebuilding certain sections to make sure that it aligns with the function or the homeostasis that is required for the body. Now, as you can imagine, there comes a time where lengthwise growth is going to be essential. So for instance, when you take a look at a toddler as they're growing into a young child, into the teenage state, into the adult stage. So what we see happening is that we need to have a section in the long bone that will allow for elongation to occur. And it turns out that particular section is going to be called the epiphyseal plate. The epiphyseal plate is informally called your growth plate. That is going to be the area where hyaline cartilage is initially deposited, and eventually as the hyaline cartilage extends and elongates the long bone, it is then replaced by either spongy bone or compact bone. But either way, it allows for the bone to grow lengthwise. Now, eventually that plate is going to close up because you're going to reach your maximum height. And this has to do with hormonal changes, also with genetics. When the plate closes up, there's no longer length-wide growth. So what we see happening is that the plate, as it closes, will leave a little remnant, almost like a little scar, so that it's easy to identify where the plate once was. And then what we're going to do is, instead of calling it an epiphyseal plate, we're going to call it an epiphyseal line. And whenever you see the line, I want you to think about the fact that this is the leftover remnants of the plate. This is what you would usually see in adults. This is basically indicating to you that this particular bone is done growing lengthwise. So now we're going to switch slowly to maintenance and remodeling for the bone. We're not going to get any taller. So here's the picture that I was promising you before. As you can see, this is my little femur, and they've given us two different looks at it. One is quote-unquote living, the other one is dried, but it wants to show you all the different components. So let's go ahead and start off with the fact that we had our diaphysis right over here. This is the shaft region. We have the epiphyses, the epi regions, which are our edges. We talked about the fact that they're going to have a covering. So if I look over to my left-hand side, I'm going to notice that I have a little rim right over here. This is my articular cartilage. Remember, that's the hyaline cartilage that I'm going to be finding at the edges of my long bone. So this is what's going to come in contact with the joints. Now, the diaphysis, as I mentioned to you before, that one is not covered by articular cartilage, but it's going to rely on periosteum and endosteum. So remember, both of these are membranes that cover the diaphysis, and the main difference is going to be its location. The periosteum will cover the outside, as you can see right here, thin little membrane, and then the endosteum will cover the inside cavity. And on the dried bone, you can really see the cavity on the inside of the shaft, and that of course is our medullary cavity or our marrow cavity. It could either be filled with yellow bone marrow, which is what we see over here, or red bone marrow, depending on if it's an actively growing bone or not. We have our articular cartilage already pointed out. We got that one going. We have our periosteum, just double checking that I'm showing you everything. Oh, let me show you the epiphyseal plate, or in this case, the epiphyseal line, because we're looking at an adult bone. So as you can see right here, I'm going to switch my colors. Here, this little line right over here, as well as one over here. You can have several ones in the same bone. At the bottom, there's another one as well. So these little white lines that are encircled in yellow, those are your bony scars, indicating the location of what formerly was known as the epiphyseal plate, the growth plate. And as you can see, they've labeled it as a line, indicating that there's no more lengthwise growing for this bone. This is found in an adult bone. So the scars are basically remnants of a previous time where they were still growing lengthwise. I also want to quickly point out the difference between compact bone, nice and solid, and then right over here, spongy bone. So you can see the spongy bone has more like little air pockets, and that's of course because the bone tissue has not been organized at such a high level as with the compact bone. Now, here's another look at how compact bone and spongy bones will stack on top of each other. But instead of looking at it in a long bone, let's take a look at it in a flat bone. So remember, flat bones tend to have a slight little curve to them. They tend to go ahead and be found in areas like the skull, as well as the sternum, the breastplate, as we previously discussed. So here you can see we have a little example of what you find within the skull bone. This is my little frontal bone. Here's my little parietal bone. And as you can see, when you zoom in, what we see happening is that it's set up like a little sandwich. You have your compact bone on the outer rim and the inner rim. And then in the middle, you're going to have a spongy bone. Now, this setup with the spongy bone in the middle as a little filling to your sandwich, this is called diplo. So whenever you see this term right here, that means one, you're looking at a spongy bone, but more importantly, you're looking at a spongy bone that is inserted in the middle of two compact bones. It is an excellent way for our body to be able to resist any type of stress and absorb shock that's being placed on the skull. So for instance, if you hit your head or you have injury to the head, the spongy bone will be able to absorb some of the shock, so it can minimize the damage that can occur. And by the way, all these little openings within the spongy bones, they tend to be lined by endosteum, the little membrane. And also, if you take a look over here, it says that both surfaces are going to be covered by periosteum when you take a look at your compact bone. So we're still using the same membranes, but we're just seeing a different setup. So the periosteum that we saw on the outside region of the shaft or the diaphysis in the long bone will cover the compact bone's outer and inner layer when we take a look at the flat bone setup. And then the endosteum, the inner membrane that we found by the bone marrow cavity, this one will take care of the spongy tissue that sits in its diplo format. All right, so if bone is considered a tissue made out of connective tissue, we have to also talk about the individual cells that are needed to make sure that everything is properly constructed, and if it needs to be remodeled or removed, it can be done so. So let's talk about bone cells. Now, there are 4 cells that we're going to need to know, and these 4 cells will do all the building, remodeling, and breakdown of the bone. So they are going to be called, you can see them right here on your slide, we are going to have an osteogenic cell, an osteoblast cell, an osteocyte, and an osteoclast. The use of the osteo preterm indicates the fact that we're looking at a bone cell. So let's see how these four rely on each other and what difference they have from one to the other. All right, so let's start off with our osteogenic cells. Osteogenic cells are a special type of stem cell. Remember, stem cells are undifferentiated cells that are waiting for the proper signal so that they can be classified or provide a specific function. In this case, the stem cells, the osteogenic cells, are waiting to go ahead and be converted into osteoblast cells. So the stem cells are called osteogenic. You find them in the endosteum membrane, also in the periosteum. It's derived from an embryonic tissue type called mesenchyme. And what we see happening is whenever they're directly stimulated, the osteogenic cells will go ahead and be transformed, or I should say differentiated, into an osteoblast cell. Now, osteoblast, I want you to think of the B in blast, and I want you to associate the B with building. Osteoblast cells are going to be your bone-forming cells. So they are the ones that are actually able to secrete the matrix and form the actual bone tissue. So over here on your slide, it says it forms a single layer of cells. You can find them in the endosteum and the periosteum membrane. They are non-mitotic, meaning that they cannot reproduce by themselves, and that is why they rely on the stem cells, the osteogenic cells, to form new osteoblast cells in a consistent pattern. As the osteoblast cells start building, initially what's going to happen is they're going to build a matrix, a background that's going to be relatively soft, and then over time we're going to do calcification where it starts to harden, mostly due to the addition of calcium minerals. Now, once the osteoblast cell is building, what we see happening is that, especially when the body is no longer growing lengthwise, your osteoblast cells will be essential for bone maintenance. And part of what it does is that it's able to regulate or monitor, I should say, how much stress the bones are being placed on to decide how thick to build the bone or how quickly to remodel the bone. Now, it will also rely on hormonal control. So as you can see at the bottom of your PowerPoint, it says that it does secrete a hormone called osteocalcin. This one stimulates insulin secretion of the pancreas. It increases your insulin sensitivity in your epiphyses, your fat cells, and that's one of the ways that your body tries to limit the amount of adipose tissue that you have within the body itself. This is all about providing proper room for the bones to grow and to develop. The hormones, this is just a quick mention of it. We'll have a whole entire chapter that we're going to be exploring all the different hormones with when we get over to chapter 18. That unfortunately won't be until we get into 2086. But for now, just concentrate on the fact that your osteoblast cells, the B is for building, they're going to be forming the actual bone tissue, first with a soft matrix, then a hardening due to calcification, and that the osteoblast cells originate from the osteogenic cells, which are going to be our stem cells. Now, there will come a time when the osteoblasts, the building ones, are done building. And what we see happening is that when they're done building, because they're secreting a matrix that will eventually harden, the osteoblast cells almost get trapped in their outside hardening process. And when they get trapped in a little lacunae, a little dip. And what we're going to do is once they get trapped, they're no longer building, just monitoring. What we're going to do is instead of calling them osteoblasts, we're going to call them osteocytes. So an osteocyte is often called a mature bone cell, and that's because it is a former bone building cell that has now become trapped in a little lacunae surrounded by the hardened matrix that it was secreted. And now what it does is instead of focusing on building, it will have monitor stress and guide the remodeling process of the bone. Do you have little canalicules or little canals that connect one lacunae to the next so the cells are able to communicate with each other? Let's see what else we have. Some osteocytes can reabsorb bone matrix while others deposit it. Oh, we're going to talk about this in part 2 of our lecture. That will have to do with the bone remodeling. But here's the statement I was looking for. Their main focus will be to act as strain sensors. So they're basically continuously monitoring how much stress is being placed on the bone. The fourth bone cell that we need to know is going to be called osteoclast. Now, osteoclast cells come from a different stem cell, so they are not part of the osteogenic cell lineage. So we had our osteogenic cells that we started with. Those became osteoblast cells. B is for building, and those became the mature bone cells, the osteogenic cells, and that, of course, is going to be monitoring the bone. Osteoclasts are the fourth bone cell that we need to know, and the osteoclast cell come from a different bone marrow stem cell. And the reason they come from a different bone marrow stem cell is because their main function is to destroy or to dissolve bone. So it's all about liquefying and breaking down the bone. In fact, the stem cells that give rise to the osteoclast are the same ones that give rise to all our other red blood cells, white blood cells, as well as platelets, all the formed elements or cell components that you find within your blood. That's just a little FYI. Your osteoclast cells are large cells. They are larger than all other of the bone cells. They have a little ruffled border, which we're going to talk about. And what they do is they use this ruffled border to increase their surface area, and they'll start secreting acidic components. And the acid will be used to dissolve the hardened matrix of the bone tissue, thereby allowing the bone to be remodeled and dissolved. Now, oftentimes what we see happening is that your osteoblast cells will work together in conjunction with your osteoclast cells. So one will build while the other will dissolve. It all depends on the level of bone remodeling as well as the thickness and the health of the bone that we are looking at. Here is a little illustration of the various bone cells. So notice how the four cells have been separated, right? So starting on top, we have our osteogenic cell. This is my stem cell that's going to give rise to my osteoblast cell. That's my bone building cell. So this is the cell that's secreting the matrix, the outside environment of the bone, and eventually it will become trapped in a little lacunae, a little dip. And at that point, it's all about managing the stress or monitoring the stress, no longer building. So we call it an osteocyte, a mature bone cell. So osteogenic becomes osteoblast, becomes osteocyte. And then for the fourth bone cell, or osteoclast, notice how they come from a different subgroup of stem cells. Notice how the osteoclast is very large in shape, and here's the little ruffled border that I was mentioning to you before. And if you take a look at the insert picture over here, you can see that it's laying over the bone tissue that's been formed, and it's dissolving the matrix. So this is how it's then dissolving and breaking down the bone, so it can go ahead and start working with osteoblast cells to rebuild it on their end. And don't worry, we're going to talk about the exact mechanism of how it dissolves. We're going to discuss that in part 2 of our lecture. Now, I inserted this little picture right here because I wanted to go back just real quickly to when we were discussing histology in chapter 5. And this was one of the pictures that you saw when you came across the bone slide. The bone slide, of course, is an example of connective tissue. And when you saw the slide, I just want to point out that what you were looking at is a transfer or a cross-section of your compact bone. So this is what compact bone looks like under the microscope. And when you look at it, it's going to look like a little tree trunk. And each tree trunk is called an osteon, as you might recall from our previous discussion. And I said to you, in the middle of it, you have your little central canal, your haversian canal. That's where all your blood vessels and nerves lie. And then now, when we look at it, I want to once again highlight these little blackened region that you see right here. And notice how they're lying in almost like a little ring format. So let me switch to yellow. See how there's like a little ring format? How they're lining up. It's almost like one layer builds on top of each other. Now, the reason they do that is because, remember, we just talked about the fact that you have osteoblast cells that can build the bone. So as the bone is building and it becomes thicker, you add another ring to it. And that space between the rings is called a lamella. And within the outer curvings of the rings, you see your little black spots that we were highlighting previously, these right here. And this right here, these little black sections that I keep highlighting, these are your lacunae. They are your little dips, your little cavities. This is where your osteoblast cell gets trapped. And then when it gets trapped, we no longer call it osteoblast, but we call it an osteocyte, a mature bone cell. So when you're looking at this picture, you're basically looking at a little dip, and inside that dip is your osteocyte. So that's where the cell is sitting, monitoring the stresses that the bone is being exposed to. And in case you're wondering, well, how do we maintain these cells? Well, notice how you have all these little black lines that are radiating out from the lacunae. I always thought they kind of look like little spider legs. These are called canaliculus. And canaliculus basically indicate that they're small little channels. And what these channels do is they allow nutrients from the central canal to travel through them to the individual lamellas and lacunae. And all the waste products can travel the other way. Once again, using the canaliculus, the waste products can travel over to the haversian canal where it can be disposed of. So that is how all the little rings, the lacunae, the osteocytes, how they're able to maintain and communicate with the central canal, because that, of course, is where all your blood vessels are located. All right. Now, in our second part for Chapter 7, we're going to concentrate a little bit more on actually what goes into building a bone and what the whole process is about. So for now, I just want to quickly just reiterate that, remember, whenever you look at connective tissue, you will often see the term matrix. The matrix will indicate the fact that you're looking at the background. And with bone, the matrix of the osseous tissue is very important because it's going to provide a lot of the strength that we rely on for the bone. It is a combination of organic and inorganic material. The organic material is mostly a mixture of like collagen, carbohydrate, protein complexes, and these will all be produced by the osteoblast cells, the bone building cells. Your inorganic material is where your calcium carbonate and your calcium phosphate salts will come into place. This will make up the majority of your matrix. As you can see, 2/3 of it will be inorganic material. So what we need to do is we need to talk about the process of calcification or mineralization, which means that we're going to talk about how exactly does it harden and provide strength to the matrix. All right, I think this picture is a nice way to end our first part. As you can see, it basically shows you just a quick reminder of how we started talking about the different ways that we can classify bones. You have your compact bone and your spongy bone. And then here it shows us from a histology standpoint. We can see, remember our compact bone under the microscope, we just saw it with the osteon and our little lacunae, our little dips where our osteocytes, our mature bone cells, are monitoring the stress. And then here on top, we see a little illustration of your spongy bone. Notice how this one looks a little bit different, and obviously that has to do with the fact that there are no osteons, no very direct organizational pattern in spongy bone, and that's partially due to the large cavities that it has. These are all the little openings that you're seeing when you look at your spongy bone. So whenever you see this image, please keep in mind that you're looking at compact bone. Spongy bone looks a little bit different due to the fact that it does not have the individual osteums. All right, I know I sound like a broken record at the end of our lectures, but I just want to keep reiterating that if you have any questions, comments, or concerns, please do not hesitate to email me, use your discussion session, stop by our office hours, whatever you choose, just make sure that you reach out to me and I'll be more than happy to assist. All right, so I guess we will talk next when we explore part 2 of chapter 7.